So in this lab, we will make a library that will teach our microcontroller to talk to us. So what we will do is we will write some code with which we will be able to send messages from this code to our computer. And it's done in the following way. Practically all modern microcontrollers have a peripheral which is called UART, or Universal Serial Asynchronous Receiver and Transmitter. And let's find on this microcontroller where it is located. Yeah, and we will turn it on. So I'll just tell you the idea. The processor has two pins, which are UART TX and UART RX for transmitting and receiving. And behind this LCD, there's actually another chip, which is called board controller. And it also contains UART to USB converter. So basically, when this our microcontroller sends symbols from UART, it can send them to the board controller, which then forwards them through USB interface to the computer. And using an application, for example, called Termite, we can receive these messages. So, okay, so in this board controller creates a virtual USB UART port on the computer. So right now I have the development kit attached. I go to Device Manager. And here I have this J-Link CDC UART port COM58. In Linux and Mac, it appears a little bit differently. You can find this information on the internet, but on Windows, it's just a COM port with some number. I don't know, if I disconnect this development kit, it disappears. So this way I know which one it is. And I have some other USB serial devices connected to these computers with number 4 and 6. But now I connect this development kit, and it appears as COM58 in my case. So in this Termite program, I can go to Settings, I can select COM58, I leave the rest of the settings like this: baud rate 115200, data bits 8, stop bit 1, parity none, flow control none, forward none. The rest I just leave as it is and press OK. And now it is connected, this application is connected to this board controller, and it is listening to any messages that this board controller will send. And it will basically just forward the messages that I sent from my microcontroller's code. So in this configuration is very popular. It is used also in Arduino and many other platforms where you have USB to UART converter, and the microcontroller just has UART, because UART is much, much cheaper than USB. So all microcontrollers have UART, only some have USB. So most people just use UART for message communication. Okay, so now we need to create a UART peripheral control in this processor and just start sending information out through UART to our computer. And let's just start doing it. Initially, I will write the code in main code, so it's easier to debug. It's in one file. And later, I will move it to a separate library so that we don't have to have all the code in the main. So to use UART peripheral in mlib, you need to open this mlib folder, browse files here, and then find USART. So this USART. Drag and drop to mlib, select Studio SDK location and click OK. And so this USART is added. So now I'll put two includes, hashtag include. To use UART, we will need 3 libraries. So hashtag include, obviously, UART em underscore USART.h. That's one. And also to use UART, we need to enable clock. So I'll write hashtag include emcmu.h. I have it 2 times here, but if you include the library several times, it doesn't matter because the second time it will just not be included. So I'll write, in full form. And also we need initially the GPIO library as well, because in order to have a pin as USART output, we need to also configure the pin as output. So I'll write hashtag include em underscore gpio.h like this. So we will actually use all 3 libraries. So in the main code, first of all, I need to enable clock for UART, but this microcontroller actually has many UARTs. So I need to go to this development kit's documentation, and I need to find which UART is connected to the board controller. And you could read all of this document and you would find where it's written. And it's called under, topic number 7, board controller. It says that there's an interface is provided between the EFM32 and the board controller in the form of UART connection. And it basically says that UART is connected to port E0 and port E1. We will be only using TX. We will only be using messages out, sending messages out. We will not be listening to messages. So this is the only thing that we care about. And another thing that on this board, we also need to switch on connection between board controller and microcontroller. The reasons are pretty technical, so that maybe you don't need UART, but you want to use port E0 on some for some other functionality, then so that it isn't connected to this board controller. There's a switch on port F7 with which you switch it on or off. So in our case, in this particular board, we need to first turn on port F7 line high so that there is a connection between microcontroller and board controller. There's a logic switch there. So first thing we need to do is GPIO pin mode set, GPIO port F, pin number 7, GPIO mode push pull, and high. Turn on switch that connects UART to board controller USB. So, this board controller. So this is the first thing that we need to do because it's written in this document. Normally, on your own custom boards, you will not have any switches between UART and the microcontroller, but in this case, it is on the board, so we have to turn it on. Now let's start configuring our UART. The microcontroller has several UARTs, so we need to figure out which one is the correct one. It has UART 0, UART 1, UART 2, UART 3, and so on. So which UART is it? In Arduino, you only have one serial port, so you don't care. It's just UART and that's it. But on these microcontrollers, so that you would be able to communicate to several devices, to several sensors through UART and so on, there are multiple of them. To find it out, you have to check out the datasheet and check out which UART is connected to port E0. So for our controller, we select documentation in this launcher view, and we will need reference manual. It's here. Oh, sorry, we will need datasheet. Datasheet EFM32 Giant Gecko datasheet. And you need to go to pin definitions, you will need to go to the package. I think it is EFM32 Giant Gecko 995. It doesn't actually matter, as we will see soon. And here is alternate functionality pinout, or just pinout, and we need to find port E0 in this first column, right? I'll double check port E0, yeah. Port E0. Maybe I already lost it. Here it is, port E0. And here it says that there is a UART. This U letter here is just short for UART. Number 0, TX pin is connected, and the location is 1. We'll use location a little bit later, but here you can see that it's UART number 0, TX pin. So we know that it's UART 0. What does it mean? It means that in our code, we need to turn on the clock signal to UART 0. So just like we wrote here, clock management unit clock enable for GPIO, here I will write clock management unit clock enable small clock sorry, without underscore, CMU clock, control space, I get this menu and I find UART 0. Take a notice, there is UART 0 and USART 0. In our case, we have UART 0. See, UART 0 and true. So we turn this peripheral on. It now starts to consume some small amount of current. Previously it was off, so it didn't use any current. Now it will start to consume some current. This is the reason why by default they're all off. Okay, so UART 0 is switched on, and now we need to configure it. And there are many, many registers for UART for configuration. Let's go to launcher and reference manual of this microcontroller. And everything about UART is written under UART portion. But its register map is the same as USART. Just USART can also be used as SPI, but generally they're almost identical. So there are many, pages that explain how it works and how to use it. That's a lot of information. But generally, I'll show you a trick how you can use it without breaking your brain. So here in register description, we can see there's a lot of registers. But again, Silicon Labs programmers have written some drivers for us so that we can initialize them in some human readable form using the GPIO and UART library. So first, there's this rule that if we want to use a TX pin for output, we need to initialize it as output. So first thing, we need to write GPIO pin mode set, GPIO port port E, pin 0, GPIO mode push pull. And initially we need it to be high. There is this rule historically that UART pins are idle high so that you can sense that something is connected to the line. If the line is low, you can make an assumption that the cable is broken, it's cut off, or it's disconnected because it's low. So by default, lines are high so that you can sense that something is connected to them. So we just set it high. Then we need to configure UART0 with some settings, and it is done in the following way. So in the mlib libraries, we can go to mlib USART, which also talks about UART. Here's even a small example. So you enable UART clock and GPIO. Historically, you had also to turn on high frequency peripheral clock. Now it's automatically done by enabling clock for UART, so you don't have to do it. And then you need to initialize it with some settings which are constructed in the form of a structure of type UART init async type def. Okay, so what I'm going to write here is I will create a structure of settings with their example settings by typing USART init async type def. And it's the structure type. Then I type the variable name. So my UART settings. Then I type equal to and curly braces open and close. And here I can control click on this USART init async type def. And I can check out what fields this variable has, what settings I can type in. So whether I want to enable the TX, RX, or both disabled, frequency, baud rate, oversampling, data bits, parity, stop bits, and so on. And even if I don't understand all of these settings, they actually have a pre-written default settings right here, a little bit lower in the code. So USART init async default settings, I can just copy them. So I select these lines, copy, and I paste them between the curly braces here. And so you can copy or you can carefully type them down. The first is, should we enable UART or not? We of course want, but we want only to initialize the TX part. So actually, if I control clicked on this USART enable, we have four options: disable, enable RX, enable TX, or enable both RX and TX. And I want only to enable TX, so I copy this, paste it here, and it says, now it will be USART enable TX. Next is what reference clock we want to use. We want to use CPU, so we just leave here 0. Next is the speed, the baud rate. In the termite, the default is 115200, and actually the board controller only accepts 115200. It's actually written somewhere in this document. So we leave it like this. Oversampling, we leave like 16. It means that actually UART will sample each level 16 times and then use the majority vote to determine whether the bit was high or low. It helps against the noise. Then we have 8 data bits, no parity, 1 stop bit. We want to leave the majority vote on, so this is false. UART is not a PSR input, no channel, just everything else just is left as default. So we actually leave the settings as they are. And then to send these settings into UART, we need to use a function called USART init async, like this. And the first argument is UART name, which is UART0, and the address of the settings. So I put ampersand sign and type my UART settings. So observe this function accepts pointer to these settings. So we put address of my UART settings. It's just the way this library is written. You just have to deal with it. There's nothing to understand. Just this is the way to write it. Okay. So UART init async UART 0, and then ampersand sign, which is shift +7, my UART settings. And after I've done this, the UART is initialized with TX on at this baud rate, and basically it should just work. We have initialized it. Now we want to test whether it works or not. It hasn't been finalized initialization yet, because we also need to enable the location. And it's sad that this thing only is mentioned in one place, but basically, to make the CPU and the chip more flexible for design, the same UART can be output on different pairs of pins, because maybe it's in one corner, you want it in the opposite corner, and so you can remap its location. So we need to tell on which pins it is. And here in the list of pins, it says #1, which means that UART is located on pin combination code 1, which is port E0 and port E1. So we need to type the following line: UART 0, then arrow, minus and greater than, route equals 2, and then this special code, which we can copy from this Giant Gecko software, which is this UART route TX pin enable, and location we will give location 0. It looks like this: UART route control space, and it gives you the options. We want TX pin to be enabled, so we use this, and we can use either or plus UART route underscore and location lock 1, because here it says that it's UART 0 TX location 1, so we have to write it this way. And this basically tells on which pins to output the signal. Okay, so this is the initialization code for UART, and now it should be working. Let's just check it out. To send a byte over UART, we use UART TX function. So let's say every 1 second, not only we want to turn the LEDs on or off, we also want to send some byte over UART. So I'll type it like this: UART TX, sorry, I think it's UART TX. So UART TX sends 1 byte over selected UART or UART that we give. So I will type UART 0 because that's the UART that we want to use. And the data, well, let's say in single quotes, in single quotations, not double quotation marks, we type in, let's say, character A, like this. So this function takes letter A and sends over UART 0 with these settings that we initialize it with. And let's just compile and see if it works. I press this hammer. Okay, it compiled. The size is 5.3 kilobytes. That's a pretty big code for what this thing does. And now let's flash it into the development kit. So I press flash to device, program. And first of all, I can look at the development kit and see that the LEDs are blinking. And I can open the termite and check out that it's sending letter A after every 2 seconds. So it shows that this code is working properly, that UART was initialized correctly, that the clock signals were initialized, that the switch was switched on, the location is given correctly, and it just sends letter A every 1 second. So the microcontroller, let's look at this board once more. The microcontroller outputs UART letter A through its TX pin, which is connected to board controller, which is behind this glass LCD screen. And this board controller receives the byte and forwards it through USB to the computer. And in the computer, I have this termite connected to this corresponding virtual COM port, and it just outputs the text that it is received. Okay. So quite simple. Now, what we want to do is we want to move all of this code to a separate file out of our eyes so that we accidentally don't hit some letters on the keyboard and damage this code. So let's build a separate library. And so in this source folder, right click on it, create new header file, and we are going to call it, for example, print. It's like printing text to the termite. Print.h, finish, and then we want to create a new source file and call it print.c. And again, in print.c, first line we write is hashtag include, in double quotes, print.h. And in print.h, we're going to copy the library names and some functions. So in print.h, we want to include the libraries, which enable us to control the peripherals. So I cut them out from here and paste there. So print.h has these em/usart.h clock management unit and GPIO header files. Then we will create a function which we will call we will call it void print underscore init void, which initializes the UART and configures it. And then, for example, we will create a function which we will call void print letter, and the argument that we receive is char L, for example. So char is a variable that is meant as signed integer, signed byte, I would rather say. So it's 1 byte. We receive 1 byte as character and it will print it out. And now let's write the implementation for both of these functions in the C file. So I delete the semicolon and open the curly brackets. And now in main file, I just cut out all the code that initializes the UART. So starting from this line, which turns on the switch that connects UART to board controller, down to the initialization of UART 0 route location, I just cut it out and paste it in print initialization code. Some code is in red now, but if you press save all, it automatically finds all the libraries and all the code, so it is not in red anymore. Okay, and printing a letter is just USART TX UART0A. So I delete this semicolon at the end, open curly braces, and cut this text out, paste it here, and instead of letter A, I will put letter L here. So basically, whatever we give to function print letter, character L, this L will be sent over USART TX UART0. Okay, so again, writing the code this way helps us because the main code doesn't care whether we're using UART 0 or UART 5. We will be just using a function called print letter, and we will give letter A, and this print library will select the correct UART and do the correct sending. And this main code, we have a beautiful function called print letter, and we can immediately understand what this thing does. It prints letter to standard output, which is comport. So, maybe for modern people, printing isn't really that good of a name for a function because we understand printing as, laser printer turning on and printing some picture or some text on a page. But historically, a function that outputs some text is just called print. And, we still use it in this way in programming. Okay, in order to use, so let's just try to compile the code and let's see if the code works and if the letter is being sent. So this is the main code. I will close these LEDs and UARTs. So in the main code, yes, of course, first of all, we need to initialize the printing. Let's say we will do it after initialization of LEDs. So I write print underscore init, right? And here is print letter A. And I'll try to compile this code. In some compilers, you will get an error, and in some compilers, you only get a warning which says implicit declaration of function print init and print letter. It's because I forgot to hashtag include the print h library. Because the library is in the same folder as source file main.c file, the compiler automatically includes all of these source files in the compilation, and it automatically finds the correct function. But the correct way to do it is that I also hashtag include the print.h library in my main file, because otherwise, the compiler wouldn't, in the strict compilation rules, the compiler wouldn't find this print init or print letter function in any of the included libraries, and it would otherwise actually give a compilation error, function not defined or function not found. So the correct way is to include the library h file in your main file, and now if I compile, there will be no warning. And the best thing is to try to write the code in such a way that you have 0 warnings or 0 problems. Okay, so now the code is compiled with improved readability, print init and print letter, and now I will flash it to the board. So I click on hex file, program, and let's see if it works or not. I clear the screen in Termite using clear button, and I see that new letter A appears. I also see that on development kit, the LEDs are blinking, changing from one to the other. In your case, they would both turn on and off. But basically the code works. That's pretty cool. So that is, a good way to write the code. However, you might obviously think that, hey, sometimes we don't want to write just one letter. What if I want to make this thing write my name, for example, Andris? If I type Andris here and try to build, I should have gotten a compilation error. I don't know why I didn't get it, but here character constant too long for its type. Large integer implicitly truncated to unsigned type. in single quotation marks, you can only put one letter and one letter only. I wrote multiple letters. Most probably this thing got reduced to only first letter, or maybe it's going to print something weird. I can try to build it. It built, and I can try to flash it, but actually the compiler should have actually given me a compilation error. So as you can see here, now it only prints the last letter of this thing because the first ones were automatically truncated or deleted. But this is actually undefined behavior, in my opinion, but it doesn't work. So print letter only accepts one letter and prints it out. We need to write a function which prints out a longer text. And to do that, we could write our own printing library, but there is this library called printf, which you have probably used. It's the most popular printing library probably in the world for C programming. Some people have already written a print library which prints out texts, numbers, floating points, strings, characters, and everything, and automatically converts them to readable form. So what we should be actually concentrating on is not writing our own printing library, but trying to link our print library to standard printing library. So in C programming language, there is this thing called printf. Print, it's a library which is able to print out letters, numbers, and strings and everything. And the cool thing about printf library, you can read about it on this C++ reference. It's located in stdio.h file, is that you can tell the printf library to output the text to whatever output you want. Either it's a display or a printer or a UART or USB output. And that's what we're going to do now. So we will link printf to our UART so that whatever we write using print is output on UART. And the problem is on different platforms, it can be different. It may be done in different ways. It's not really universal because it's low level, but for Silicon Labs, Silicon Labs programmers have written a middle layer between UART and printf, which we will use, and it is used in the following way. So they have written a code which is called Retarget IO, which allows us to tell that printf should be output to UART0. And we need to first get the code into our project. The code is located in Simplicity Studio installation library, and we can just copy it into our project, but we need to find it. And it's hidden a little bit, but I'll just show you where it's located. So on your mlib folder, right click and click Browse Files here. So you are now in Silicon Labs Developer SDK, Gecko Studio, Suite versions 2.7, platform mlib source location. But we will go a few levels up. And we need to go, I think it was in hardware, kit, common, drivers. And here is the retarget IO.c. Okay, so you can just look at my folder's location in your Simplicity Studio installation. It should be in the same place. So it is in Gecko SDK Suite version 2.7, hardware, kit, common, drivers. There's this file retarget IO.c, and you can just copy it with Control C and click on the source folder and Control V, paste it into your project. It was also copied into your project folder automatically. So now you have this retarget IO.c file, and it is, you can open it and you can read through it. And it's written in such a way that if you create functions called retarget write and retarget read, it automatically connects those functions to printf standard libraries, printf API. So it is defined in the following way. In your code, you need to write the following lines. I think it is int retarget write. I think it was, let's see. Oh yeah, here it is. Actually, in this retarget IO.c file, in the first code lines, it says the names of the functions. So let's just copy them into print.h and paste it here. Delete the external, because this external keyword says that somewhere else these functions are defined, and this is the place where they are defined. So this is the place, we delete it. And retarget read char wants to read 1 byte from UART, and retarget write char wants to send this char over UART, and returning 1 means success, and returning 0, I guess, means that it was unsuccessful or something like that. Let's see. It's actually, its return value isn't even being used. So if we create functions with these two names, then printf will send out bytes using this write char function, and scanf will read chars using this function. So we just need to copy their names and write implementation. So our code will not support reading a character from UART. So here I will write return 0, but it doesn't matter, because if we don't call scanf function, then this function is never actually called, so we don't care. And this write char, basically we can just copy USRTX UART 0. Instead of L, we send out C, and return, I guess 1 is the number of characters that we sent, but I don't really remember. Okay, let's see the implementation of retarget serial.c from their example code, and the tx, what does it return? Here it returns the same character that it was sent to send, so it's a bit weird, but fine. We will just return 1, that we sent 1 character, so everything is okay. And we don't need this print letter anymore. Okay, so let's recap. In our print.c file, we created functions called retarget read char and retarget write char in this following way. And we send this character over the UART that we selected and return 1. In print.h, we created the names for these functions. We copied the retarget IO.c file into our project source folder. Here it is. And this results in the following thing, that in our main code, if we also write hashtag include stdio.h, and after we have initialized print init, in our code, we can write the following code. I'll write it in the loop. For example, printf hello world. And at the end, I put new line so that every time it's written in new line. And printf is a function in stdio.h, which accepts 1 character, million characters, numbers, and whatnot, and automatically formats them and sends them over whatever this retarget right char uses. So in retarget right char, I can send it over UART. I could also delete this line and send it over USB or SPI or display, doesn't matter. So this is why it's pretty cool. Now, so this is the main code. I will build it and let's just check out if it works as intended. So the code size increased again from 5 kilobytes to 9.4 kilobytes because printf library, this stdio library, is actually pretty heavy. It's pretty big. So, you know, it uses around 4 kilobytes of memory, but it allows you to print texts and numbers, so that's what you pay for it. Just you have to remember that, for example, you cannot use a microcontroller with 2 kilobyte memory and printf library. It's impossible. There's not enough space. But our microcontroller has 1 megabyte of internal flash memory. So these 4 kilobytes is nothing. It's 0.4% of the entire space of your microcontroller. So you don't have to worry about it. So I build it. I flash it into the development kit. I open Termite, I clear the screen. As you can see, the LEDs are blinking, and also hello world text is being printed out. Okay, so this thing works. Now, let's try to run an example code from printf C++ reference just to see how it works. Okay, so I'll just copy all of this information and I'll just put it right here so that you can see some examples how to use printf. If you have been programming previously, you obviously know printf library very well, but just let's recap. So you, in your printf, you type the text, whatever you want, for example, characters. And then when you put percentage sign and variable type, then this printf will take the argument, convert it, and print it out in the format that you say. For example, percentage sign C means print this variable as a character. So if you type double quotes A and percentage sign C, it will print it out as letter A. And since letter A in ASCII table is number 65, so even if you write percentage sign C and number 65, it will automatically just print it out as a character A, because in ASCII table, letter number 65 is capital A. Okay, it will be the big A. So if you want to write a number, you use percentage sign D for integers. And for here example, 1977 will be written out as 1977, which is exactly what you want. But here, number 65, if you use percentage sign C, it will not say 65, but it will output a capital letter A. So there's the difference. Percentage sign C prints out letters, percentage sign D prints out them as numbers. And LD means that this is a long number. Probably you don't care about it because this is a 32-bit system where all numbers are long unsigned integers. So whatever, but there's just this specification. So preceding with blanks, if you write percentage sign and then number, then you set the minimum width of the number. If the number is less than 10 characters, then blank spaces will be put in front of the number 1977 such that the total length is 10. So if this is a number that consists of 4 digits, then 6 spaces will be put in front of it so that it's constant with 10 symbols, and it is usually used for, some formatting of on-screen numbers in columns so that the columns are aligned. Some old way to do it, but fine. Then if you want, instead of blank spaces, to prepend zeros, then you write percentage sign 0 and then number 10 and then D, and it will put 0 0 0 0 0 0 1977. Then different radix. This is percentage D means it's decimal. Percentage X means that it will be output as hexadecimal number. So it will be automatically converted from 100 to 64 in hex. Percentage O will convert it to octal with base 8. Percentage hashtag X, I don't know what it does, this hashtag symbol, but it is written in printf library, and it says if you put hashtag in front, then use with specifiers the value is preceded with 0, 0x, or 0x respectively for values different than 0. So basically this hashtag automatically adds 0x in front of your number, or 0 in front of octal number. Then you can also print floats. You write percentage sign F, it will print out floating point number. But if you set percentage sign 4, it means the minimum width is 4 for entire number. And dot 2 says write only 2 decimal letters after the dot, because by default it prints out 5 decimal letters. So 3.1416 will be written as 3.14160. But now it will automatically round to 3.14. So dot 2 rounds the number to 2 decimals. Percentage sign 4, percentage sign, where it is. Minimum number of characters to be printed. Okay. There is also with trick and string. Percentage signs S prints out a string, null terminated string. So let's just compile this code, and let's see. Okay, it's 9.8 kilobytes, and let's just flash it and see what the output is going to be. Okay, clear. And let's see. So I will pause the input, but let's check out. Characters were printed correctly, small a and big A. Decimals preceding with blanks, as you can see, spaces before the number, zeros before the number. Then you have decimal, hexadecimal, and octal, and 0x in front of hexadecimal number, and 0 in front of octal number. That's the historic way to write it. We just have to accept it. But floating point numbers are not being printed what's going on here? It says floats, and then it tries to print out floating point numbers, and nothing is printed. Okay, width is fine and string is fine, but why aren't floating point numbers printed out? So actually, in embedded systems, for example, in this ARM GNU C compiler, by default, printing floating point numbers is disabled. It's impossible. The library doesn't do it because working with floating point numbers is a very heavy task for microcontrollers, especially microcontrollers that don't have floating point unit. Multiplying floating point numbers is really, really hard on 8-bit or some simple microcontrollers. This is why floating point printing is disabled. Also, floating point numbers are stored in memory in this special manner, which is, let's see, float. Way of writing, computation float, single precision, computer number. So the floating point numbers are stored in this IEEE 754 format, which is the following. So instead of just writing the number, in some random way, the first bit is sign, then there's exponent, which tells to what power to raise the fraction, and then comes the fractional part. So actually, floating point number consists of 3 parts, and this is why it's not so easy to convert floating point to decimal, because you need to take this number and raise the exponent and then multiply and then add the sign. And also, floating point arithmetics are not that simple on a regular microcontroller. They would need to be converted to integers and so on. So floating point operations are by default in print library switched off. Since our microcontrollers are pretty powerful, they are 32-bit processors and with relatively high speed, we can also turn on print float in the following way. Right-click on your project properties and go into C++ build settings. And here we have, I think in our GNU linker general part, click print float. So initially it is switched off. And if we check this box, we tell the linker that it is okay to link the print library in such a way that it prints float. We understand that it will take more time and more space in our microcontroller to print float, but in our case, we can afford it. So we click print float enable and click OK. And now, if I recompile the project, let's check out. The size of our code increased by 10 kilobytes because printing floats takes 10 kilobytes. Before it was 9 kilobytes, now it's 19. This is why, for example, usually when you use microcontrollers in embedded systems, oftentimes you try to use as small a microcontroller as possible, and maybe you don't have 10 kilobytes lying around to enable floating point print. This is why it has to be switched on separately. But now I compiled it. I flash it to the microcontroller. I open Termite and turn on the communication. And as you can see, floating point numbers are being printed now. 3.14 plus 3 exponent 0, 0, 3.141600 e plus 0, 0. So they are being printed, but it takes more flash. This is why it's turned off by default. Okay. So, yeah, so print is working. it's outputting the text to Termite. So it looks like everything works pretty well. So I'll now again show the print.c file. Here you can pause the video and type it down correctly. This is print.h file, nothing much going on here, but still type it down correctly. And main.c, also it almost fits in one page like this. So now you see the entire code. And you can type it down and check out that everything works, okay? Type it down, compile, upload, check out that you read output on Termite. And once you've done it, just save the code and upload it to Artus, okay? So that's it for today.